I'm Will Benton. I work in Red Hat's Emerging Technology Group, and today I'm going to talk to you about some work that my team and I have done on using Spark to look at community dynamics in open source communities. And we're going to look at sort of a definition of the problem. We're going to look at the data source we're thinking about, which is the FEDORA messaging data. This is operational data related to the FEDORA project. We'll look at some issues we ran into ingesting bulk data in the real world. And then we'll look at some analyses we ran on these data. So the first question I want to ask is, what makes a great open source community? Obviously, we see a lot of open source projects, but you need more than just a GitHub repository with an appropriate license to make for a good community, right? A community draws together people from different backgrounds with different motivations, all working towards making a project and a community a better place for contributors and users. So who here has never heard of the FEDORA project? Okay, so most people are familiar. FEDORA is a Linux distribution that's built on 3 primary and 4 secondary architectures. There are 17,000 packages in the most recent release of FEDORA. We have tens of thousands of contributors, millions of users. And as you might imagine, there are a lot of components in FEDORA's infrastructure that have to be working together perfectly to manage a project at this scale. When someone builds a new package, the testing service needs to know about that. When someone creates a new account or becomes authorized to package software for FEDORA, those changes have to notify other components as well. And making all of that stuff work at scale is an interesting problem. So we'll talk about how FEDORA solves this problem, which is FEDORA messaging. Instead of having a bunch of services that communicate together via ad hoc interfaces, and you have this sort of M-to-N coupling of things, there's simply a messaging bus. And almost every component in the FEDORA infrastructure both writes to and reads from this bus. So as an example, if I am building a FEDORA package and I add a new patch, adding a new patch to make that package build in a new release of FEDORA will generate a message. Updating a wiki page will generate a message. Building FEDORA for a secondary architecture, like S390, or building an alternate collection of packages, those things will also generate messages. If you've used IRC, if you've seen IRC meetings before, you may have seen a IRC bot that manages IRC meetings. That will issue a fed message when the meeting starts, when the meeting ends. If you run the meeting, you get a message. If you vote in a meeting, you get a message. Koji is FEDORA's build tool, and when a build starts, there's a message about it. When a build completes successfully, or when a build fails, there are messages about those things too. And then there are a whole bunch of web services that users interact with that also generate and read messages. The one I want to call it in particular is Bodhi, which is the FEDORA QA tool. When a build completes and it reads a message off the bus from Koji saying that the build completed successfully, that build is available both for automatic testing and for community testing. And so all of the things you can do with testing become messages as well. So these are all things that primarily produce these messages. So you can see that a lot of operational details about the dynamics of this community are stored on this, happen on this messaging bus. Some things that primarily consume these messages are a number of sort of fire hose-like interfaces to a stream of messages. If you use IRC, you could go to FEDORA-fed message on Freenode and see FEDORA messages as they happen. There are also command line tools and a web gateway to just inspect these messages as they happen. You can sign up to get notifications about messages related to your username or messages related to a package you maintain. And there's a project called DataNommer that warehouses and archives all of these messages. So there's always a bunch of bulk data to look at. And finally, a sort of a fun example, FEDORA badges is sort of like video game achievements, but for the FEDORA project. So there's a state machine in a service somewhere, and it gets updated by reading messages related to each user. And when your state machine hits certain targets, you get a little digital icon on your page. This is what mine looks like. So that's sort of a fun application of this infrastructure. So I'm going to talk about some of the problems we ran into with bulk data ingest and how you can work around these in similar applications. But first, just there are sort of three sources that Fed message data are available through. The first is that bulk historical data from Datanommer, which is a PostgreSQL dump. You can access specific historical records through a web interface, and you can subscribe to the live stream through 0MQ. So this is really nice for Spark applications because you have both the batch and streaming aspects. You can train a model on bulk data. You can update your model with data generated since the last bulk data you exported, and you can subscribe to the live stream and process events as they happen as well. So this is what the main table in that PostgreSQL dump looks like. And as you see, there's some common metadata for every message. There's a timestamp. Messages are signed because anyone can write to or read from this messaging bus. It's really open source. There's a message topic, category, the application that produced it, and then we have a bunch of different kinds of message. Each has a topic-specific payload. Well, we put that all in the database by storing it as a text field. And there are a lot of different approaches to saying I want to cram a bunch of heterogeneous data in a single relational table. And a common thing to do is say, well, we'll just serialize it as JSON. But as the joke goes, now you have two problems. And Spark makes it really easy to deal with JSON ETL, but there are still problems you can run into, and most of them relate to schema inference. So we'll talk about those now. The first problem we saw with schema inference is when you get a schema that's too wide. And because Spark schema inference is going to take a collection of objects and find the schema that will apply to all of them, sometimes you get a schema that's too wide to write useful queries against. In this case, we're modeling a zoo, and we have an object called animals. But this isn't really an object. It's really a map. It's a map from animal names, duck, zebra, and platypus, to an object describing some characteristics of the animal. Now, the platypus has been confounding schema inference in real life for a long time, but this zoo application does not have to. If we give this to Spark SQL, it will give us a data frame that has an object called animals that has a duck field with a mammal field, a bill field, an egg field, a zebra field, and so on. That's not really what we want to write queries against. Instead, it would be better if our maps looked like a list of key value pairs, because then we have a fixed schema for each element in this array, and we can write more useful queries or find another way to sort of normalize these data and deal with it. The other problem we ran into with schema inference is when you have schemas that diverge, when Spark SQL can't give you a useful schema for data. And the place we saw this is where we had objects that had the same field with different values. So this is a simplified but real example from FedMessage, where in FEDORA, branches can refer either to a specific FEDORA release, or they can refer to a Git branch in the package source code management. So here we have one kind of branches field that's an array of strings, and another kind of branches field that's an array of objects. And what Spark SQL will give you here is it will just sort of throw up its hands and say, I'm sorry, I can't do anything useful with this, but I can give you the JSON strings for each branches field, which is also sort of a pain to write queries against. This is better than what it did 6 months ago when it would just crash, though. So a way to work around all of these kinds of issues is to pre-process the JSON values that are in your source before you try and infer a schema. And a really great way to pre-process JSON is to use the JSON4S library. If you like writing Scala and you like partial functions, I like both of these things because I like only having to worry about the cases I care about. You can use JSON4S to pre-process your records. In this case, we're saying if we have a branches field with an array of strings, we're going to rename that. So it's called package branches. If we're going to have a branches field with an array of objects, we're going to rename that so it's Git branches. And in this case, we don't have that conflict anymore. We don't have a diverging schema. So now that we have this data ingested, and we've worked around some of these pitfalls you run into with real-world rich data, we can look at actually analyzing the data we got from the FEDORA community. And here's a distribution of message counts. So on the right axis, we have the users that have at most the number of messages on the x-axis. And note that the x-axis is a log scale. So we see this kind of distribution in a lot of sort of project participation contexts, but you notice that 80% of users have 10 or fewer messages. Now, if you look towards the right, you see that there are a few users with millions of messages, right? Those users with millions of messages are all people who maintain Fedora on a secondary architecture, and so every 6 months they run hundreds of thousands of builds, and that's why they're so active in the project. A slightly more interesting thing to look at is the number of unique topics per user. And in this case, we see, again, about 80% of users have 4 or fewer unique topics in the Fed message history. But the thing that I really like about this graph is that because of the way we extracted this data, we were looking at 40 different topics. And you see that no user actually had 40 different topics. You have some users with 22, 23, 24 topics, but no one does everything. So this, to me, is actually a really nice indication of a healthy project. You have some people who do a lot of things, but you don't have anyone who can't go on vacation without causing the project to grind to a halt. So moving on to an actual learning application here, we had the idea to characterize users by the sets of unique message topics affecting them. And the idea here is that we could use machine learning pipelines and transform these arrays of unique topics to sparse feature vectors and then use that for learning. And I'm not going to go into a lot of detail on this. There's a link at the end of the slides that will show you some, a fully annotated version of this, but this is the bulk of the transformer that goes from an array of topics to a sparse vector. And it's really nice to write these kinds of things for machine learning pipelines because you're basically just writing code that changes the schema of a data frame and adds a column to the data frame in this case. So looking at an actual problem, now that we have these featureized users with topic sets, can we say which of the users has a topic set that makes them likely to be a Fedora packager sponsor? A Fedora packager sponsor is someone who's responsible for mentoring new packagers to the Fedora project. So because there is actually a logistic regression implementation for machine learning pipelines, this was an easy classifier to try. And it had actually about a 1% prediction error rate, which sounds really great until we consider that about 1% or a little less than 1% of Fedora users are packager sponsors. So we could have actually done better by just predicting everyone wasn't a sponsor. This is something you see in these problems pretty frequently. So we had actually a really low true positive rate with logistic regression, which was sort of a bummer. But building a decision tree worked a lot better than logistic regression because it sort of teased out the interdependent features. Topic sets aren't really independent variables. And it identified on the leaves of a decision tree that these message topics were likely to predict that someone was a Fedora packager sponsor. And these were obvious to me as someone who uses Fedora and works with Fedora. The first one indicates that someone's role in the project has changed, which can include adding an account. It can also include becoming a sponsor. The second one indicates that someone has updated their user information. And since sponsors are responsible for helping the people that they've sponsored on the Fedora project, they're also more likely to be someone who updates their information to say that they're on vacation or indicates what time zone they're in or the best way to reach them. So again, these are leaves by themselves. They don't predict that someone is a sponsor, but they were the ones that were most likely to predict on leaves. So that's some things we've done with these data so far. There's really a lot of interesting stuff there, though. And if you're interested in looking at this some more, there are some next steps you can take. The first thing you can do is you can go to fedmessage.com, which will explain FedMessage in more detail than I did and give you links to even more sort of cool applications. My team at Red Hat maintains a library called Silex that has a bunch of code factored out of internal Spark applications we've developed and includes some helpers for applying JSON transformations to RDDs before you ingest them. And then the top post on my personal blog right now has links to a bunch of this stuff, as well as to some more in-depth articles that cover some of the topics I covered in this talk in more detail.